G'day, Mr. Bennett here. Today we're going to be looking at the concept of a motion in a straight line, and what you'll need to do there is work out equations for displacement, which is, in this case, it's given to you. And then what you do is your first derivative, and that will give you the velocity equation, and if you do your second derivative, you get your acceleration. Alright, so these questions sort of lead you through what you've got to do. Now, the first thing I would do if I'm doing this is to graph this on a graphics calculator. So I've done that, and you can see this particular thing, obviously t being 0, you don't have negative time. So starting below the origin, okay, so I'll be left of the origin, moving up to the origin, then I'll be turning around, I think, at 1 second. And then you can see it's going to turn around at 2 seconds, and then it's going to go in the positive direction or to the right. Okay, so you sort of match the motion. If you think about that being up and down, one dimension, that's what we need to be thinking about here. All right, so if we start doing what we need to do with this equation, so in part A, what we need to do is we need to do our first derivative. So our velocity equation, our v of t is in fact s dashed of t. And so when you do that from that equation there, you're going to get 6t squared. Now you need to be working in t's because it's being presented in t's. 18t plus 12. Alright, so now if you take out a common factor of 6 there, then you'll get t squared, take 3t plus 2, and so therefore what we can see is when that's equal to 0, we're going to have t take 2, t take 1. Okay, so we get our turning points. So when v of t equals 0, we get our critical points. So therefore that occurs when t is equal to 1 or 2. In other words, when v of t is equal to 0, no velocity, it changes direction, doesn't it? Okay, now if we do our velocity sine curve for that, alright, so do our velocity, so it's v of t, and that's a function of t over here, and we need to consider the points of 1 and 2. Now, the key thing is here, we know that t has to be greater than 0, doesn't it? So 1 and 2. Now, we have to do our sine diagram for that. Now, there's a couple of ways of doing that. You can either do it from your curve, okay, or you can do it from here. So if I pick a value, say, between 0 and 1, say 0.5, 0.5 I get negative, 0.5 I get negative, so two negatives will make a positive, okay. Then if I've got a value between 1 and 2, so 1.5, so that will be negative on this side, and that will be positive on the second term, so that will give me a negative. Then pick a value greater than 2, say 10, 10 take 2 is positive, 10 take 1 is positive, so that will give me a positive there. Okay, so that's my sine curve. I'll do the same thing here with the acceleration. My acceleration is in fact the second derivative of that, or it's the first derivative of the velocity equation, and that will give me 12t take 18. Okay, so again, bring out a common factor of 6, that gives me 2t take 3. So my critical points when t is equal to 0 for this thing over here, for my acceleration equation, is going to be 3 on 2, which is 1.5. Okay, again, I can do my sine diagram, pick a value, say 1, that's going to be negative, pick a value greater than that's going to be positive. Now, we'll talk about how you can tell that from the sine diagram. Okay, we know at this point here between 0 and 1 it's got a positive tangent, it's got a negative tangent, it's got a positive tangent. So therefore that's my little secret. How to tell there, here's my point of inflection at 1.5. At this side here it's concave, so that's going to be negative. Here it's convex, which is going to be positive. So I know that's going to be true, and it matches with what we'll be working on later on. Now, we haven't done all this work yet, so we'll be talking about those terms. So in part A, I've actually done my sine diagram for that. Find the expressions and draw your sine diagrams. Find the initial conditions, okay, in part B. So obviously we're looking at S of 0, we're looking at V of 0, and we're looking at A of 0. Alright, so when we put 0 in there, we get negative 5. And I think we're working in metres. Let's work in metres here. When we go to A of 0, it's centimetres, by the way, not metres. Okay. V of 0 is going to be 12 centimetres per second. And put there, it's going to be negative 18 centimetres per second squared. That one there, sorry, is wrong. It should be to the minus 1. So it's minus 12, it's 12 centimetres per second. Okay, so what's going on here? That's the initial conditions. Does it say describe the motion? Find the initial conditions. Quite often what you'll do is you'll describe what's actually happening there. So at this particular pace, at t equals 0, it's 5 centimetres below or to the left of the origin. It's moving to the right at 12 metres per second and centimetres per second, and it's decelerating at 18 centimetres per second squared. So it's moving that way, but it's slowing down. Okay, that's what would be happening there. We need to work out what's actually happening at time t equals 2 seconds. Right, so we can do the same sort of thing here. Right, so S of 2, you put it into the equation, B of 2, you put it in there, and A of 2, and you just do the same thing here, and you work out the value and you describe what's happening. Now, if I'm going to do that, right, could I be blowed doing the calculations? Probably. Let's do it on the graph. Okay, so if I do, just to save some time, just put 2 in there. So my S of 2 is negative 1. Right, so it's negative 1 centimetre. Right, we know at 2 it changes direction, so we know it's 0 centimetres per second. And when I put 2 into there, that's going to be 24 take 18, and it's 6 centimetres per second squared. Alright, so you only get marks for doing your answer, so you don't really have to show all the working out there. Alright, and it says describe the motion of the particle at t equals 2 seconds. Alright, so that's a bit like what we did before. So you'd basically say in D, it is it's 1 centimetre to the left of origin, our imaginary place that we base everything from, and stationary. So you'd say it's turning around, can't you? Turning around and accelerating. It's accelerating to the right at 6 centimetres per second squared. Alright, so that's describing what's going on with that particular particle. Alright, the next part of that question says find the time and positions when the particle changes direction. So that's actually part D. Well, changes direction when V of t is equal to 0, and so therefore it changes direction at t equals 1 second and t equals 2 seconds. Alright, so that's when it's changing direction. Now we have to find the position for that. So if we go back to our graph again, Right, we found that's -1 for 2. If we did the same thing over here for 1, we can find that 0. Okay, so they're the two positions. So at t equals 1, we know s is equal to 0 centimetres, and here we know s is equal to -1 centimetres. Alright, so that's what we've got from that. Again, using our technology and our graphs is a really good idea to save time. Draw a diagram to illustrate the motion of the particle. Okay, alright, so we'll do that. So part E. So if we just have a straight line, sort of straight line. Okay, we know it starts, we'll put our origin here. Okay, that's our origin. We know it starts initially at t equals 0. We know it's at this position here, and that's at a distance of -5 centimetres. Okay, that's where we're starting there. So it goes in this direction here, and at 1 second it's at the origin. So it goes there, and it changes direction. Right, so therefore if we label that point there, t equals 1 second, s is equal to 0 centimetres. We know that somewhere in our curve, right, it goes and changes direction at t equals 2 seconds again. We know that that moves back how far? It moves back 1 centimetre. Okay, so that point there, we know at t equals 2 seconds, it's actually at a distance of -1 centimetre. And then what it does, it changes direction again, and then it goes off in that direction. It will go off in that direction forever. So we need to put arrows there to show the direction, okay, what's actually going on there. Now, one of the sort of questions that you might get asked is, you might get asked to say, how far has it travelled in the first 5 seconds? Okay, if it did that, then you'd have to work out how far it is at t equals 5 seconds, and you can add that section to that section to that section. So that's the sort of question that you might get asked, and I don't think it's asking us in this particular case. Okay, so we've done that to illustrate there. Determine the time interval when the particle speed is increasing. Alright, I need to talk about this because this is an important concept. I've drawn these particular sine diagrams, so these things here are sort of parallel to each other. They're lined up. Okay? Now, when we have the same sign, when these things have the same sign, then the speed's increasing. When the signs are different, the speed's decreasing. So here, if you're looking at our velocity, it's got a positive sign there. That's got a negative sign. Okay, in this section here, I'll have to do this bit here as well. In this section here, that's got a negative sign, and that's got a negative sign. Okay, in that section there. In this section here, it's got a negative sign there, and it's got a positive sign there. And here it's got a positive sign and a positive sign. So if we're looking at that, this section here, they have the same sign, and in this section here, they have the same sign. Okay, so we can talk about the speed increasing for t equals 1 to 1.5 and t greater than 2. Alright, so let's just do that. So part F, okay, so the speed is increasing for t greater than 1 and less than 3/2, and when t is greater than 2. Right, obviously the speed's decreasing on those other times. Now, the other thing they often ask you in these sort of questions is to talk about the velocity. Okay, so when's the velocity increasing? Well, to get our velocity, we get it from our acceleration equation. So our velocity is from our acceleration equation. Our speed is from using where these two things line up. So if I said to you, when's the speed increasing? Well, that would be when velocity is increasing, would be when it's positive. That would be when t is greater than 1.5 or 3 over 2. The velocity is decreasing for between t equals 0 and 3 over 2. All right, so speed and velocity are slightly different terms. All right, and those people that are in physics will probably understand that. But that's the sort of question that you will get asked. All right, so again, speed increasing when they have the same sign, velocity increasing when it's positive, velocity decreasing when it's negative sign. You get that from the acceleration graph. So that sort of takes you through most of what you have to do for this type of question. There are a number of things. If I just talk about this one here, this equation here, if you do your sine diagrams, what you'll find is most of the things in here, if you have velocity and your acceleration, the point where it changes direction is when t is equal to 0 or less than 0. So in that particular case, you don't have to consider that. You either say it's positive or negative, all right, because of the sine diagram, all right. So remember, in these particular questions, the time must always be positive, all right, or 0. So it's got to be realistic in terms of what you're doing. So good luck with those questions. I think you should be able to get through them okay. And obviously, if you need some help, ask one of your classmates or catch up with me.